I know you're going to be hearing a diverse set of talks. Today I'm going to be talking about the science of memory, largely from a cognitive neuroscience perspective. And I hope along the way, some of the content that I share in terms of the new discoveries and what we can do with neuroscience in exploring memory makes contact with some of the problems that you're sort of thinking about and trying to make progress on. So when I think about memory and I think about my favorite quotes surrounding memory, this quote from Chuck Klosterman is sort of my favorite sort of quote, because it gets across the way in which the knowledge that we acquire through experience allows us to go beyond the immediate present, and in some sense augmenting our intelligence beyond that which we sort of have in the immediate moment. So Klosterman wrote, most people, this was in a review of the movie Memento, most people consider forgetting stuff to be a normal part of living. However, I see it as a huge problem. In a way, there's nothing I fear more. The strength of your memory dictates the size of your reality. And it's that last sentence that really, I think, gets at the heart of what memory does for us as cognitive agents. It allows us to transcend the immediate moment and that which is going on in the immediate moment, to bring knowledge from the past forward and use that knowledge to inform how we might be thinking, behaving, acting, et cetera, deciding and acting in order to optimize the outcomes. And so when we think about memory, we're thinking about memory sort of stretching this sort of the size of our reality. It's sort of memory that's allowing us to sort of travel through time beyond the immediate moment. And there's this notion of sort of we have experiences at some point in time. We're building knowledge. We're building different kinds of representations. And we now are traversing through time, and we're in the present. And at that point in the present, to the extent that there are cues in the environment that allow us to make contact with the knowledge, the states that we had in mind and brain in the past, we can kind of reactivate them and bring the present mind and brain into a state that resembles essentially traveling back to the state in which we were in the past. We can then use that knowledge from the past in order to sort of know how to know how to sort of behave and act. And so from the psychology of memory, there's long been this notion of memory as mental time travel. And what I want to share with you today is the advances that we've been making in neuroscience in terms of being able to sort of characterize the mechanisms that give rise to different forms of learning and that underlie, in essence, this mental time travel, essentially neural time travel, traveling to the brain state through time to situate ourselves at some point in the past in order to inform the present or perhaps the future. Okay, and so what I'm going to be focusing on is just advances in neuroscience and cognitive neuroscience that sort of point to some of the mechanisms that allow us to stretch the sizes of our current realities. Okay, and when we think about memory, and we think about memory for the kinds of things that many of you, not all of you, Martha was talking about how she was trying to condition your response to that song, and so it's a particular form of memory. But for many of us, we care about sort of conscious memories of life events or the knowledge that we've accumulated across numerous life events. And what we know in terms of at least, one thing we know about the neurobiology of building memories for events, many of you have probably seen this in loved ones who have perhaps have Alzheimer's disease and are robbed of their ability to acquire new memories and build new memories. We know that structures deep in the temporal lobes, the hippocampus and cortical structures surrounding the hippocampus, are fundamental for us to be able to build memories, for us to bind together the multifeatural sort of experiences that constitute an episode. So we know that the medial temporal lobes allow us to sort of perceive and represent complex stimuli and sort of bind them together, build memories of the conjunctions of those stimuli, such that we can leverage those memory representations at some point in the future. So if you sort of think about this a little more mechanistically, though still in a sort of abstracted cartoon way, when we're talking about remembering of events, we're talking about fundamental mechanisms within the medial temporal lobe, within the deep parts of the temporal lobe, including the hippocampus, that build these conjunctive representations during experience. So many of you traversed here to campus today, perhaps on a bike or car, and you ultimately have the experience of sort of placing your vehicle in a particular location on campus. That's a multi-featural experience. There were the ideas, the thoughts you had, maybe thinking about, boy, how am I going to get here into Arriaga? You're paying attention perhaps to where you put your bike or your car, et cetera. This multi-featural event has the various features of the event are being represented in different cortical regions of the brain, and it's ultimately the funneling together of these different pieces of our experience into the hippocampus and learning within the hippocampus to build a pointer, a conjunctive memory representation that allows us, that's essentially the heart of episodic memory. That's the heart of building memories for single events. The hippocampus building these conjunctive representations that are capturing the co-occurrence of these event features. And these representations are flexible such that at some point in the future you get out of here and you think, where's my car, where's my bike? You can use that retrieval cue as input to the hippocampus into the medial temporal lobe, and to the extent that it makes contact with the stored trace, and the hippocampus can pattern complete out, can reinstate its pattern, the hippocampus is thought to be able to drive information back out into cortex, flipping the state of different cortical regions back to the state in which they were in, or some variant of the state in which they were in during the experience. And it's this information that you use to guide, to make decisions and guide how to act, okay? And ultimately lead you to where your bike or your car is, hopefully. So what I'm going to do in my 39 minutes is first sort of tell a story about, throughout, I'm going to tell a story about how neuroscience has just advanced tremendously since I was a graduate student and came here and was fortunate to be part of some of the first functional imaging studies of the brain. I'm going to describe ways in which advances in neuroimaging combined with combining those data with machine learning, pattern classification, and other kinds of algorithms has allowed us to really advance understanding of how it is the brain acquires knowledge, the various forms of knowledge that are acquired, and the ways in which it then allows us to reinstate, bring that knowledge to mind, okay? So first I want to just kind of begin, and I'm getting now pretty old, my hair is gray, my ears are a little longer, I don't know. Going back to the very first study that I was part of, back in '95, this is what we did. We're talking about functional brain imaging, taking healthy individuals, putting them in a standard MRI machine, and recording indirectly measures of neural activity as they're performing, as they're learning, and as they're remembering. And so we're getting measures of neural responses during the learning stage, during the remembering stage. And back in '95, when this all started, we could collect data from a single slice of the brain every 6 minutes or so. We had very impoverished data. And so a paper would look something like this, where we only have a little bit of data from a little bit of the brain. Today, we're doing whole brain imaging, rapid acquisition of whole brain data. We're feeding the data into pattern classifiers, and undoubtedly you've read and you've seen the popular press that we can figure out, we can decode what the person's seeing, what they're looking at, what they're thinking, perhaps reconstruct from their brain patterns the visual image that they happen to be looking at, et cetera. We've come a remarkable way, remarkably far in just about 20 years or so. The work I do is conducted actually here in the Quad. We put in an MR facility in the basement of Jordan Hall about 5 years ago, and we're collecting sort of whole brain high-res data, and we're sort of combining our brain imaging measures of learning and memory, again with these sort of multivariate analysis techniques to answer various basic science questions. I'm going to start just as a teaser to just kind of illustrate the kinds of things we can do and how far we've come, just by sort of showing and addressing this question, well, can we use brain data? Can we look in an individual's brain? Can we look at an individual point in that person's brain state and know whether or not they have knowledge of something, if they remember the thing they're looking at as having been encountered before or not? Can we read out memories from the brain? And how well do we do? So we and other labs have been doing this now in the last few years, and the take-home story is in highly controlled situations, we can do remarkably well. So here's a very simple study. Individuals come into the lab, they encounter individual faces one at a time, and that's each of those faces is the learning experience. So they encounter a whole bunch of people, a whole bunch of images during the learning episode, and then we put them in the MR scanner, and we're collecting these functional measures as we present them: previously exposed faces, old faces, and new faces that they didn't see. And we're recording for each one of these faces at the time of retrieval, we're recording whole brain data, patterns of activity across the entire brain. And we take those patterns of activity and we feed them into a pattern classifier for two different kinds of conditions, two different states. We want to know, we can address many things, but what I'll share today is we want to know, is the brain state, when somebody is looking at a stimulus that they've previously encountered and they recognize it as old, is the brain state qualitatively different than the brain state when they're looking at something new, somebody they haven't seen before, and they're perceiving the person as novel? Okay? And so we're taking whole brain data, and we're taking a subset of them and using them as training data sets, and we're taking brain patterns associated with old items that were recognized and new items that were perceived as novel. We're training up a multivariate classifier to try to discriminate between these two sort of states of the brain. And then we're taking single test patterns, single volume of brain data from an individual subject. We're feeding it into the classifier, and we're asking, by just having those data, can I know whether or not the person has memory for the stimulus that triggered that pattern of activity? Can I decode whether or not they're recognizing something or perceiving it as novel? So basically feed in the test pattern, the classifier makes a probabilistic prediction as to whether it's in state A or state B, and we can see how well we do. The long and the short of it is here's each of these points is a subject in this experiment, and here's sort of the mean. Overall, doing nothing special, we're well in the 80%, where empirically derived chance is 50%. We can look at individual brain patterns from an individual brain and know with well above chance accuracy whether or not the person has knowledge for the thing they're looking at, whether they recognize it or perceive it as novel. And moreover, these classifiers, they feed out probabilistic predictions, and so we might sort of, if we care about this with respect to applications, such as in the law or something along those lines, and I'm not advocating, I'm not a proponent of sort of rolling this kind of stuff out into the real world at this point in time, but classifiers are making probabilistic predictions, and so any particular brain pattern might be a good example, a weak example of a particular brain state, or it might be a pretty good example of a particular brain state. We might want to know, well, if we just listen in on when we have strong patterns of activity in the brain for state A versus state B, how well do we do in terms of detecting or decoding whether somebody has a memory? And here you can see, on average, over our sample of 16 subjects in this study, we're at 95% accurate when the evidence in the brain is incredibly high. So here's a case where, with modern day brain imaging and computer science sort of statistical approaches, we can look at brain patterns in very controlled situations and know whether or not somebody has knowledge. Okay? That was for a very simple situation. What about something more complex, real-world episodes, which are temporally unfolding, play out over a little bit of periods of time? So we had 16 undergrads on campus where these Vicon Review digital cameras, early generation version, and they were just wearing these cameras for a few weeks. The cameras are automatically taking photos as they detect some change in the input, motion, light, et cetera. And so we ended up with about 45,000 photos for each subject, and we distilled those photos down into approximately 180 what we thought were relatively distinct events that had played out over that person's life for 3 weeks. And we took just a subset of photos, 4 photos for each event, from that person's camera or from a different person's camera, and we presented them to the subject. And we wanted to know, do the brain patterns elicited by photos of your own personal experience relative to photos of somebody else's experiences, are those brain patterns qualitatively different? And again, can we read out knowledge for these rich autobiographical experiences? And there, we didn't have to do anything special. Across all trials, on average, we were approaching ceiling. And there's signal related to memory in many parts of the brain. You can look and you can feed in signal from areas in the frontal cortex, the parietal cortex, temporal lobes, many parts of the brain are signaling and carrying evidence about memory, somebody's memory state, whether or not they're having this subjective experience of remembering versus perceiving something as novel. For me, it's been 20, 21 years since our first study, but I would never have predicted we'd be able to do this kind of stuff. And who knows what the next 5, 10, 20 years are going to bring, given the rate of discovery over the last 20 years. So that's kind of a basic sort of teaser that modern day neuroscience can do a lot in terms of detecting knowledge in an individual brain at an individual moment in time. What we want to do now is sort of talk a little bit about what we know about the learning mechanisms that support the acquisition of different kinds of knowledge, and then how that sort of particular kind of knowledge, sort of event memory, what the mechanisms are that allow us to do this neural time travel and sort of reinstate features from the past. So we don't need to get lost in the neuroscience details. All I care to emphasize in this particular slide and sequence of 2 slides is that the learning problem, there are multiple learning problems that we as organisms face. And my colleague Jay McClellan, amongst others, have made the argument that different problems have different solutions. One problem is to extract the statistics and extract the deep structure across a whole set of experiences and to sort of accumulate that knowledge. And that the mechanisms that might sort of do that sort of knowledge extraction and sort of learning are at odds with the ability to hang on to knowledge about single isolated events, single experiences. And when single experiences are different from the central tendency of our experiences, if you have a mechanism that's sort of extracting that central tendency and that deep structure, you can lose the details of individual experiences. So there's this argument that we have complementary learning systems, one system to extract the central statistics and the deep structure, and to throw away the individual experiences, sort of idiosyncratic information, and another mechanism that builds unique memories for one-shot memories for events. And the idea here is within the medial temporal lobe, and this is you don't need to worry about the neuroanatomy, but there's an initial set of cortical regions in the medial temporal lobe that receive the input from most other cortical regions of the brain. These regions and cortex more generally is learning about the individual features or items of experience. It's going to allow us to essentially learn over those various items, as we'll see in a moment. But we're building knowledge of single features, whereas that knowledge might allow us to recognize something as having been encountered before. And that this is different from what's happening in the hippocampus, which is building knowledge about the unique conjunctions of features. So you can build knowledge about this feature over numerous events, but you might have a conjunctive trace that is capturing knowledge about only a single association between an item and its context, and that can pattern complete out that single moment when this item occurred in that context. And from a learning mechanism perspective, it's been argued that the cortex, in order to support these sort of item representations, is slowly extracting the statistics over our experiences over one class of items. And it's going to assign, therefore, similar representations to similar stimuli, whereas the hippocampus is sort of orthogonalizing. It's rapidly forming these unique representations that are essentially pointers to single memories. And these two kinds of traces allow us to do different kinds of things. They allow us to remember in different ways. Okay? We can now probe this with functional imaging. One approach that we've taken is to record data when people are encountering experiences, when they're learning, and ask the relationship, what's the relationship between brain signals and patterns during learning and later memory outcome, and different kinds of memory expressions, later memory expressions. Can we look at individual brains, look at individual brain states, and know whether or not the person learned from that event or not, and what kind of memories they built from that experience, okay? And I'll skip over this slide other than to make the point that part of the story is engagement of frontoparietal, attentional, and sort of cognitive control or executive function networks that fundamentally alter what features of an experience are attended to and laid down in memory, and how we're sort of strategically working with our experiences and our memories. But a big part of it is the medial temporal lobe, the hippocampus and the MTL cortex, where there is a predictive relationship between the strength of neural signal in the medial temporal lobe and later remembering versus forgetting. But moreover, if you probe for later memory for individual items, or for the association between the item and the context in which it was encountered. So collect brain data as words are being encountered in one of two different contexts, probe their memory for the words. Do they recognize the item or fail to remember it? They forgot it. And if they recognize the item, do they have memory for the context in which the item was encountered, or they just recognize the item alone? Turns out in the medial temporal lobe, consistent with this two learning system model, the cortex is building knowledge of the individual features or items. Here, items that are later recognized, irrespective of whether they're going to remember the context, whereas the hippocampus is building representations of the unique co-occurrence of the item in the context, okay? It's also the case that we can now use imaging and this approach, but also certain forms of pattern classification analyses, certain kinds of pattern analyses to characterize the similarity of the brain patterns evoked during learning to the brain patterns evoked from all other kinds of events, and ask the question, is cortex assigning similar neural representations across events, and the hippocampus is assigning unique representations, and the degree to which there's neural representational overlap in the cortex versus distinctiveness in the hippocampus, that's predictive of later remembering of different forms. And we've recently sort of pushed this tested this prediction of the cortical versus hippocampal learning algorithms, also using functional imaging, where the complementary learning system is basically saying you're going to have a better memory in the future if your hippocampus has effectively established a differentiated, unique memory trace. Its pattern, its neural code is different from the other neural codes for the other experiences. Whereas in cortex, you want to basically be at the center of the cortical, of the representational distribution. You want the neural trace of an event, of an item you're going to later recognize, to kind of be in the center of the statistics. It turns out if you look and you analyze brain patterns using that are collected with fMRI, brain patterns coming out of the hippocampus and the MTL cortex, the more distinctive the pattern is in the hippocampus during an event. The more unique it is, the higher the probability you'll remember that event. In the cortex, the more similar the brain pattern elicited by an event is to all the other brain patterns elicited by all the other events, the higher the probability you're going to remember that event. So we have evidence for two different learning mechanisms, one in cortex that's building summary statistics over experiences, and a mechanism within the hippocampus that doesn't want to throw the trial unique details away, wants to allow you to sort of capture and build a trace for that unique moment in your life. And these two different kinds of memories support and allow us to do different things. They support different kinds of memory judgments. All right. What I want to do now is sort of describe a little bit more the way in which this hippocampal kind of memory allows us to do this sort of neural and mental time travel. What does it mean for us to remember a specific event from our past? And for me to run into and see Byron's face here right now, and remember running into Byron at the local gym, and he was on the rowing machine, and sorry for revealing details, but to bring all that back to mind. There's nothing in that sensory input right now that carries any information about this gym, a rowing machine, or anything like that. How is it that my mind and my brain it's been able to accomplish this mental time travel and bring this other knowledge back to mind? Okay. And here's sort of a cartoon version of the cartoon version I presented earlier. We're having some experience. I'm in this gym with Byron, and I've got these sort of multi-featural these various features of the event represented in different cortical regions, each represented in a distributed pattern of neural responses, neural ensemble. This information ultimately is projecting in onto the hippocampus, drives a population of hippocampal neurons to fire at that moment in time. They rapidly wire together, and it's this hippocampal trace that if you lose it because your medial temporal lobe isn't working because you have Alzheimer's disease, you can never glue things together. You just have these isolated bits of experience, but you don't remember having had that discussion 5 minutes ago with your loved one. You never glued those things together because you could not build one of these pointers in the hippocampus. And these pointers then I see face, makes contact with a stored representation. The hippocampus reinstates its neural ensemble, and it inverts. It drives the state of these various cortical patches back to resemble the states that they were in during that experience that I had with that stimulus. And it's this sort of reinstatement of content back out in the cortex that is, in fact, the content that I'm using to remember this past event. Those are the details I'm bringing back to mind. What evidence is there for that? We are now at a point where we can do this at the individual subject level, at the individual trial level, where we can measure the reinstatement of cortical patterns at the time of retrieval, the reinstatement of the patterns that were present during learning, and we can show that this reinstatement relates to people's memory experiences and depends upon hippocampal cortical interactions. Okay, so here, really quickly, we're now able to measure, kind of quantify the strength of cortical reinstatement, the degree to which the brain state today has traveled back, given that retrieval cue, and gone back and resembles the brain state from that past event. And we can relate this to behavior, and we can relate it to hippocampal computations as well. So the trick is largely the same. We're collecting whole brain data as people are encoding different kinds of experiences. The experiences contain different content, such as, say, faces or places. And their brain patterns then in, say, visual cortex associated with representing faces out there in the world or representing landmarks, buildings, et cetera, out there in the world. And we train up a classifier to essentially learn about what the visual cortex response, the perceptual representations are like for these different kinds of experiences. And then we can validate that the classifier, in fact, has learned about these different brain states, learning over different kinds of content by feeding and left out learning patterns and see how well we do. But critically, we can then feed in a retrieval pattern. When somebody is cued to remember, do you remember having seen or thought about a face? Do you remember having seen or thought about a place? We can feed in activity in the cortex at the time of retrieval and ask into this classifier that only knows about brain states at the time of learning, and ask, what's the similarity between the brain state at retrieval and the brain state at learning? Can I decode and know what the person is remembering by feeding in the brain pattern when they're remembering into a classifier that only knows about what they experience, what the kinds of things they experienced, okay? If you do this, so here's the one study, words paired with famous faces, words paired with famous landmarks. During learning, during the perception phase, if you feed in the brain patterns and test the classifier, we're near ceiling in terms of being able to look in visual cortex and know whether the person is looking at a face or looking at a landmark. What happens now at test? You just give them the words and say, hey, tell me what you saw with this word. Was it a face? Was it a place? If you remember the face or the place, can you tell me the specifics, or you just know rough, the details? It was this category, but I can't tell you the details. My memory isn't that vivid. Well, if the person gets the retrieval cue and they say, I have no idea, when you look out and look in visual cortex, there's no evidence in visual cortex that they've brought back to mind a representation of a face or a place. When the person says, I don't have memory, there's no evidence in their cortex for any of that sort of memory. So to the right of this is the degree to which the cortical pattern looks like the pattern that was encountered during learning. What if they say, yeah, I know I encountered a face or I encountered a landmark, a building with that thing, but I don't have all the details. The cortex now has evidence. The evidence, the degree to which the cortical pattern at retrieval looks like the pattern during face learning is higher. If the person says, yeah, I can remember I saw a face with this, but I don't know the details. My memory is not that vivid. What if they have a vivid memory? They can tell you all the details. The strength of cortical reinstatement is even stronger. The cortex looks even more like the cortex looked during learning. So there's a tying together between these sort of re-expressions of cortical patterns when we're remembering and our subjective vividness of memory. Also, there's a relationship between these patterns and how accurately we are in our decisions. So here's just a related study. People are imagining, they're given a word and they imagine a person or a place that might be described by that word, and then later on, and you can decode the patterns when they're, and differentiate between imagining people and places. And now later on, they're presented the word and they're trying to remember, what did I think about this item? What did I imagine? Can we read out from the cortical patterns, can we read out what they're remembering, and how does the strength of cortical reinstatement relate to behavior? And it turns out there's a pretty strong relationship. The more the cortex looks like the pattern that was present during the initial experience, the more accurate the person is in their memory expression. And co-occurring with this is hippocampal signal. Greater hippocampal activity at retrieval is associated with more accurate remembering. It's also associated with faster decisions. That is the information. Hippocampal triggered cortical reinstatement is the information we use to make memory decisions. It's the content that colors our subjective qualities of memory. So not only are we seeing this relationship between hippocampal activity at retrieval and memory accuracy and decision reaction times, but the stronger the hippocampal signal at retrieval, the stronger the cortex has flipped back to look like the pattern that was present during learning. Kind of tying this whole story together. Okay, actually a little further ahead than way ahead of where I thought I would be. Guess I'm going quickly. All right, so we've got evidence now for this one form of memory, one form of knowledge building, which is hippocampal dependent building of associations between the multiple features of an experience, and then hippocampal triggered replay of pieces of that knowledge back out in cortex that we use then to make decisions. The last thing I want to leave you with is some work that we've begun to do, gluing together functional imaging and multivariate sort of analysis approaches with pseudo virtual reality. I know there's a lot of interest in VR here. Getting true VR experiences into the MR environment is fairly challenging, so we have sort of first-person sort of gaming style paradigms that we've begun to use with Jeremy Bailenson as a colleague. And I just want to describe one such study that we've completed because it makes a fundamental point about memory. Everything I've been talking about right now has kind of taken this flavor. When we talk about memory historically, we think we're talking about the past, right? Ways in which we're trying to bring knowledge of the past forward to deal with some situation at this immediate moment in time. But memories are, in essence, memory is sort of essentially prediction. It's acquiring knowledge through experience that allows us to build a better predictive model about the world. And that allows us to sort of predict both what is relevant in the immediate moment in time, but perhaps to run forward models, to predict about what kinds of things we might want to do in the future in order to accomplish our goals, okay? And so while we've often talked about sort of memory as a sort of mental time travel, time travel back in time, we in fact know that memory is fundamentally about being forward-looking. For those who, as I have experience with various loved ones, have loved ones with medial temporal lobe impairments, such as in Alzheimer's disease, you know that in some sense there's this restricting of the size of their realities, not just about what they can kind of remember at the immediate moment in time, but the ability to sort of plan, to run these forward models, to sort of prospect about what you're going to be doing 5 minutes from now, an hour from now, next week, et cetera. That kind of goes as well. And so we know that memory-based simulations about things we might want to perform, ways in which we might prospect about achieving future goals is really an important sort of role and power that memory gives us. So recently we've begun to sort of try to to take on this question and explore whether or not we can kind of look at brain mechanisms of perspection using the methods that we have, pseudo VR combined with brain imaging. An example task that we have is that we've turned to is sort of a prospective spatial navigation paradigm. And so many of you undoubtedly engaged in memory-guided perspection. Some of you have likely been here before, or at least on campus before, and in thinking about coming here, you might have drawn on memory and said, well, I'm going to be coming down sort of Palm Drive, and I'm going to hit this sort of sub-goal, I'm going to hit Campus Drive, I'm going to turn left, I'm going to go into that parking lot, and then I'll wander over, right? So you're using memory while you're at home to simulate, to prospect how you're going to sort of navigate through space. And we wanted to, in a very simple first study, ask whether or not we can sort of detect patterns associated with those different pieces of perspection. Can I, when somebody is sort of in a virtual environment, can I read out from their brain patterns where they currently are in that environment? When I cue them to travel, to plan to travel, to navigate through that environment to a goal, can I read out from their brain patterns what their navigational, their goal is? And moreover, can I read out what route they're going to take to get there while they're in place just planning, okay? Sorry, I see I failed to appreciate my animation here. All right, so what we're going to care about is, start knowledge, goal knowledge, and sub-goal knowledge. And we basically want to know whether or not we're at a point where we can use modern-day brain imaging and various techniques to sort of detect these different kinds of states of the brain and different aspects of knowledge the person might have as they're planning some future act, okay? We brought subjects in, and we basically, we used a paradigm that actually has been used in rodent studies, looking at hippocampal dependent memory. We scaled it up. Our subjects are in a large outdoor arena. They're on this sort of track. They're on a circular track. And they're learning through free navigation. They're learning that there are 5 relevant locations which are sitting at the heart, at the center of these ellipsoids. There's 5 relevant locations on this big track, and there are distal cues, there's mountains and various other things out there in the environment. And so they build up knowledge of their environment, and they know that at each of these locations, too, there are a couple of sort of abstract visual stimuli that appear at the goal locations. And we're going to use those stimuli to now cue them, now that once they've built knowledge, we're going to cue them to plan to navigate through this virtual environment, okay? So first they build knowledge of the environment, and then we're scanning them during this planning period where we present them one of the cues for one of the 5 locations, and we instruct them, this is your goal. They're in a particular location in that environment when they get that cue. They get the cue, and they know 10 seconds from now, when I'm released from a holding period, my task is to navigate over to that location, okay? Here, they're doing nothing. They're presented the cue for a brief period, and then they're looking at the road. Every single trial, all they're doing is looking at a fixation and the texture of the path that they're on. And we want to know, can we read out from the brain patterns at this moment in time where they currently are in space, where they're planning to go, and given that for more distal cues, there's a shorter route and a longer route, can we read out, they almost always take the shorter route, can we read out evidence that they're mentally simulating, they're reinstating, they're bringing back to mind the sub-goal locations along with the goal location, okay? So they're here, they're at any one of these 5, could be the start location, they're cued to mentally prospect where they're going to go, and can we read out evidence for where they are, where they're going, and the route they're going to take, this route rather than that route? And the long and short of it is, the answer is yes. It's not just within the hippocampus, within the medial temporal lobe and other brain structures. We can decode from their brain patterns, they're in a virtual environment, we can know where they are in that virtual environment at that moment, significantly above chance. We can further train a classifier not to know where they are in space, but what their goal is, where they're planning to go. And this is now, what we see is they're over here, but the evidence on a classifier trained on their goal state, the evidence for the correct goal location, the correct location, is significantly greater than any of the other possible locations. They're sitting here and they're planning to go there, and we can read out the pattern of activation of that spatial code of where they're planning to go. And moreover, the evidence for the sub-goal is significantly greater than the evidence for the sub-goals on the alternate route they don't take. There's significantly above chance evidence for this path they're going to take that they're mentally simulating. We're excited about this because it allows us, this is sort of a basic sort of somewhat, there's a underlying sort of theoretical point, but it's a basic sort of first proof in principle because it's going to allow us to address some things that my lab has been very interested in for a while. One, I've been talking about episodes as isolated events. We, over the last sort of decade or so, have become very much interested in the possibility that these same mechanisms of cortical reinstatement, hippocampal triggered replay, if they occur during some experience that is unique, that's novel, but that partly overlaps with some past experience, if that replay of that past event occurs during the current event, that allows me to weave together an autobiographical history of experience, relating experiences and things that never co-occurred together, but that through hippocampal-dependent replay allows me to build this integrated memory representation, essentially building structured knowledge about the relationships between things that never co-occurred. And my lab has some very simplified, non-real world sort of experiments where we've kind of demonstrated that, and we want to sort of now move it into a rich sort of paradigm setting, such as this VR setting, where you can imagine people understanding and building structured knowledge and maps of their environments and the relationships between places in their environments where they never went from location A to location B, but through replay mechanisms, they begin to build this knowledge structure in mind. So we're interested in that, and we're interested in sort of the ways in which pre-existing structure, pre-existing schemas allow for more rapid learning and integration of information into those schemas, and spatial schemas are very powerful for that, allow for generalization and flexible behavior. And then the final thing is we've become very interested in the ways in which, while stress has many benefits for us, it also, very high levels of stress can take offline these sort of hippocampal-dependent perspective mechanisms and make us sort of more dependent upon sort of overlearned habits and how So things like economic stress, health stress, actually have a snowballing effect because they take offline this powerful sort of learning and memory engine that allows us to prospect and to flexibly use memory to plan and to achieve our goals.